Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome back to the same math time and the same math channel here at twitch.tv/NLMathman and at 1 p.m. Newfoundland Standard Time. All right. Today we're on day 52. Boy, oh boy, we're really climbing up there, aren't we? 52 streams so far. Behind me today now, we've got a picture of another iconic part of St. John's. This is maybe the lesser known or the lesser seen of the views. Hold on a second. Sorry about that. This is probably the lesser seen of the views from the top of, well, not really the top, but the sort of the edge of the city over by Signal Hill. This is just down from there near what we call the battery, or the battery fortifications, right? And here we have a Brobdingnagian pan flute here behind me, which is this, is something that I called this thing in the past, which I think is quite funny. It's a good word use of some literate terms, right? You got to put your degree to use somehow. Hey, if it's not going to put it to use at work, you might as well put it to use recreationally. And for me, it's breaking out the Brobdingnagian. It's a good word. Look that one up. That's a that's an one to add to your lexicon. Sort of file that one away back in the old gray matter someplace. I mean, pan flute's an okay phrase too, but like, yeah, whatever. We don't need that kind of stuff. This is example of, yes, some of the battery fortifications in St. John's, and there's quite a bit more than this, of course, and this is more a I don't know, more of a memorial, I suppose, to the whole setup than it is like an actual faithful recreation of the setup. But like I mentioned yesterday on stream, um, these weren't entirely just for decoration, right? There was actually conflict and fighting in Newfoundland or in over the island's history. Though, of course, as being in North America, we've been away from the destructive conflicts of modern memory, right? But down in the middle right, sort of there, up up right here, you see that? That is Fort Amherst. You can just see that, and that's on the other side of the Narrows, because just down past this hill that we're looking over here now, there's the Narrows, right? The entrance to the St. John's Harbor, and that over there is Fort Amherst, which is named after Lieutenant Colonel William Amherst, who was the British naval commander that sort of liberated St. John's from the French in the final battle of the Hundred Years' War, right? Which was it was fought between the English and the French all over North America, largely in Quebec, and then in the Newfoundland afterwards. And it marked the third time that the French successfully attacked St. John's, because there was never much of a garrison of British troops stationed here. They sort of claimed Newfoundland and then ran off to do stuff elsewhere in Canada and sort of left St. John's to the merchants, which is the merchants and the fishermen, right? Which is really indicative of the town's history. St. John's is a weird little like this libertarian anomaly on the side of the world, sort of, right, where there wasn't even really a centralized government, because it was, like I mentioned before, because it was um, forbidden for there to be local governance for hundreds of years, and it was ruled by I mean, nominally administered by the captain of the fishing fleet, right? So what ended up happening for the way the town grew was there was no central planning whatsoever. It was just, whatever merchants were there to trade fish between the larger fleets and the smaller fishermen, trade from the inshore fishermen to give to the Europeans who were bringing it across the ocean. They just sort of set up shop and made their own rules. They made their own roads. They made their own, everything was kind of just, I guess, grew in an organic sense, but in a very unplanned sense, very much different than a lot of communities in the world. Anyway, the history of St. John's is to me extremely interesting, not just because I've lived there for so long, but because it is such an anomaly when it comes to just the way that the city grew and was established, right? But here we do see, like, looking out over the reason why people settled here in the first place, or one of the reasons, was because of this harbor, and these fortifications were extremely important in. Anyway, I could ramble about this for ages, but I mean, this is not really what people came here for, if indeed people come here at all, right? Insofar as people do tune into the stream, they're not tuning in to hear me talk about St. John's history, though, as much as I would like to. Over on the side here now, we've got some topics that I'm going to get to today. right? I'm going to talk a bit about standard deviation, about the introduction to it and how to calculate it. I'm going to do a bit of sine law intro and then some angle properties review. Okay. I think first up, I'm going to go over, I'm actually going to do this in reverse order of what it says here. I'm going to do the angle properties review first. So Renetta, like I said earlier, I'm going to go over this on stream, you know. So here we go. We're going to go over, all right, there we go. So this is now going to be math. What is this? 1102B. This is going to be unit, what is this? Unit 2. Right, I'm going to do, like I mentioned before, I'm going to do question 8 over here. Okay, 59 degrees there. 60 here. 47. 73. Unknown. 65. 25. And an unknown here. But we know this whole set is a right angle. And this is Z, and this is W. Okay, so from what we've got here, we do have plenty now in order to determine all the angles that we don't know. Right? We've got loads and loads and loads of info that we can use to figure out all of these ones. So say we wanted to figure out angle Y, right? Well, angle Y is super duper simple, right? Because we're told this part down here in the corner, this one over here, right? This is a right angle. So if this is a right angle, we know that right angles are 90 degrees. So we know that the Y is going to be 90 minus 25. So Y is going to be 65 degrees. They're like so, right? You know, I mean, to be honest, like if you don't know how to get that one at this point in this course, I think you really got some reviewing to do, right? Because we know that it's 9, even though this is 25 and this is an unknown one. Like I've been doing these on stream so often, right? That I think that yeah, I don't know, being unable to get some of these ones is a little bit strange, right? Seems to indicate that maybe people should be using some of the resources I'm giving them. So that's going to be 65 over there. X up here, we know that this whole thing, this whole section here is 180, right? So we know that X is going to be 180 minus 65 and minus 73, right? So 180 minus 65 is going to be 115. 115 minus 73 is going to be 62. I'm just gonna not gonna be so proud as to not use a calculator there. 180 minus 65 minus 73. 42. 42. What was I saying? 62? Boy. Look at me. 42 degrees. All right? So X then is going to equal 42 degrees. I'm going to write those in blue as I fill them in after. And we don't even need to find this one over here, but now we are totally able to find this one, right? Because of the 180, there's a 180 rule for here and a 180 rule for the full triangle over there, right? But again, right, like these are all super simple rules. All we're using is that a straight line is 180. We're using that a corner is 90, right? If it's marked as 90. And then this one over here, this is You see, Z here is inside a triangle with a 45 and a 75. So we know that all three angles in a triangle add to 180 as well, right? So Z is going to be 180 minus 47 and minus 73, which is going to be 180 minus 110, right? Which is going to be, let's see, 60, 120, 60 degrees. 60 degrees there for Z, right? And now again, we've got 120, sorry, 180 here because this is a straight line, right? So then W equals 180 minus 60 and minus 59. So W is then going to equal 61 degrees. Right? And this is a review for the unit, right? So, I mean, I'm going through this fairly fast because this should be fairly basic for you at this point, right? Because we've been doing these topics repeatedly, and this exact question a whole bunch of times as well. And all the rules that we did here were the super simple ones, right? Not even any of the parallel lines or any of the alternate interior or any of that kind of stuff, right? This is just knowing that this symbol here means 90, knowing that a straight line is 180, knowing that a triangle is 180, and then again knowing that a straight line is 180, right? So if you are approached with a question like this or had to approach a question like this, you need to do it piece by piece and then use that to determine what we're doing for these ones, right? But again, this should all be just review to you. Right now, I do go over these separately for every single student that I have, right? So you may have noticed if you were watching that I have done these exact questions several times before. That is because these are being done like individually for students that need them, right? So the resources are there. They're definitely there to learn this material and to be supported, being supported as much as possible, as much as in class, right? So realistically, right, these questions are all fairly straightforward and should be just as easy as when you're doing them in a physical school. So here now we can't actually really determine x here because we're not told that any of these lines are parallel. So if you wrote as the answer that this one is impossible, I'd honestly give it to you. I'd give you the marks for that one because for it to be possible, we need to know that this line and this line are parallel. But as soon as those are parallel, we know that x and 119 are alternate interior. We know that alternate interior angles are equal, and therefore x is equal to 119 degrees. So they are the same? Yes, the Kevin, yes, they are. They are indeed the same. So these ones are alternate interior, which sort of makes like a Z shape. This one's inside sort of the crook of the Z in both cases. So those ones are going to be the same. Okay, one other one I wanted to do here on stream now for this. Remember the Z and F trick? Yes, the alternate interior angles. Yes, that's right. Right, because if we have an F as well, right, if we had an F like this angle and this one here, those would be equal as well, provided that this line and this line were parallel. Now let's see. Am I going to? Now I tell you what. I'll splurge. I'll splurge a bit and use some more paper here, right, for question 10, because question 10 is a rather large one. AB and DF, I would say, are parallel. Ah, good eye. Yes, those ones are going to show to be parallel. AB and DF are indeed. That's right. And we'll see why here now shortly. Oh, how are you doing? I'm doing fine. Yeah, it's doing pretty well out here. Keeping on busy, keeping doing some work. I don't know. Distance teaching maybe has seemed to drag on a bit for people, but you know, it is kind of the new normal at least for the next while. Because as far as I know, we are going to be online doing this until January, right? As far as teaching goes. So, yeah, I haven't heard otherwise yet, but so far as I know, teaching like what I'm doing here is going to be sort of in this online format for for quite a while yet. So, doing pretty well, adapting to it. Let's see what we got here. Are there any lines parallel in 10? And we'll see, other than the two you stated, yes, I believe there's one other pair of parallel lines, but I'm pretty sure we just have two pairs of parallel lines here. But we will take a closer look now in a second. Now, let's see, is that everything filled in? Okay, so one thing that we can do here now is start filling in some of the other angles that we weren't given from the start, right? And I'm going to fill some of those in I'll use green. GH and KL? Yeah, there you go. So we know that this angle here is 107, right? Which means we're going to know this one is 107. And we know this one here, right? It's got to add up to be, this has got to be a 73, and this has got to be a 73, like so, right? This one's a 73 over here, which means this is a 73. This is a 107, and this is a 107. Okay, so it's looking like DF and AB are parallel, right? Because KL is one transversal. It's a transversal that goes across it. And we see that all the angles around here, and all the angles around here are the same. Uh, training at training my math algebra is still iffy, but I read the postulates of Euclides. These lines and shapes come more natural to me. Yeah, yeah, I do. Geometry does have a very good sort of spatial component, right? Like if you're used to I don't know, various spatial awareness or reading maps or anything like that, something like lines on here can be a lot more intuitive, perhaps, than say the algebra skills, right? Because algebra is, of course, like a language. It's like a written language with its own grammar and its own syntax. This sort of has a grammar as well in a sense, but it's visual, right? It's more so than literate, I guess. So this one is, we know this one's 107 and 73 over here. I'm just going to fill in as many of these that I can as well. We know that's 73 because they're opposite. This is 107 because it's opposite. This one over here is going to be a 107. This is going to be a 73, and this is going to be a 73. We know that. Okay. So because okay, so we know now that um, AB is parallel to DF. All right, so just to write out a bit what we mean here. So the angles around transversal GH, so this transversal here, those ones are equal. And then the angles around KL are equal as well. I want to train my physics and math. Found a new hobby, astronomy. The way better at biology is it requires a certain reductionist view and is more broad. Love to do some amateur astronomy stuff. Yeah, yeah. Astronomy is kind of fun. Yeah, yeah. as a kid, I had this little book for like constellations and stuff. It was really, I mean, it's super basic astronomy, just for observations. But when we'd go camping, I'd be able to, away from the light pollution and stuff, right? Able to break out a little small telescope and see different constellations, which is super fun. But astronomy is incredible. Yeah, it's amazing that say when people discovered astronomy, like started seeing patterns in the night sky, just realizing those patterns, people were able to take that and use it to navigate their ways across oceans and things, right? Like it's incredible. It's incredible the ingenuity that people have to see, even ancient peoples, right, saw these that there were patterns and consistencies with the way the dots appeared in the night sky. And all of a sudden, hey, we can use that to navigate places, to know where we are in relation to, where we've been, sort of thing. Right? Yeah. Yeah, astronomy like that is really interesting for sure. Okay, let's see if we can find another pair of lines that are going to be the same here, right? Well, by the same token, now we also know that GH is parallel to KL. It was nice catching up again. Hey, thanks very much for dropping by, Kevin. Yeah, it's great, good talking to you. Right? So basically, because we have everything around this point is equal, this one, and this one, we have those four, and all those angles are equal. What that kind of means is these four lines here, these form a parallelogram, or a shape where this side is parallel to this side, and this side is parallel to this side. Right? Another way we can think of a parallelogram, like if we look at, I'll just circle them, right? The red circled angles make a parallelogram. Right? So we've got this one, this one, this one, and this one. Right? Those add together to be 360, which is what the interior angles of a quadrilateral are going to be. And also these two here, opposite ones are equal. These two opposite ones here are equal. Right? Now, I mean, even just glancing at it, even if we can probably see that, say, line CD is not going to be parallel to DF or AB, right? But just to sort of prove that it isn't, right? We can go through and we can say, well, this one here is going to be 107, this is going to be 107, and this is going to be 73. And yes, those are the same values as some of these other ones, but we can see now that they're switched, aren't they? And like if we look at this section here as a four-sided figure, well, we've got 106 here, 107 here, 73 here, and then 74 over here, right? Because that's 106. So those four there, we know that this line and this line are not parallel, right? Because the angles, if they were, these two angles would be equal and these two would be equal. There's loads of different ways we can approach a question like this. We could look at it like as a series of four-sided shapes as well. Now the other question, perhaps a more relevant one, would be, is IJ parallel to GH or KL, right? Because we know, I mean, even just from the diagram, we know that CD is not parallel to AB or DF. But is this one parallel to this or this? Well, we can figure that out by looking at this point, this point, and this point. And if all the angles around this one are the same as around this and around this, then it is parallel. And if it's different, then it's not parallel. So this is going to be 106 here, right? This is going to be a 74 here, and this is going to be a 74 here. So it's almost there, but it's not. So we know that this one, IJ, is not parallel with GH or KL. right? So this one is a good summary of some of the different things that you've done so far this unit, right? But you don't really need to say that part. You do need to say all you need to say to get full marks is this bit and this bit, right? So this and this, the black underlined parts, that's all you're going to have to say to get full marks on that question. Okay, so let me go back over to my intro screen here. Stream is not starting soon. Yeah, so that was angle properties review. Next up, I think I'll go in reverse order of what's shown over here because the last topic is the most significant, right? Standard deviation. So I'm going to do a brief sine law intro here now. Now this is for Esther's next course. She's going to get to once I finish correcting the test of the previous one. But I did do a video only a while back. I believe it was stream 32 on this exact topic. And Esther, I linked you that one already today. I am going to do a brief um, look at this topic again here now because I want to show it to you using the exact guide that you've got. So this one over here is the Math 3102C guide that you have. And I'm going to just really quickly introduce sine law. It's a nice summary of two of the different topics that we've done, the trigonometry and then also the similar shapes. It's got links to both those. Math 3102C Unit 2. So then sine law So sine law can be used to find missing sides or angles in triangles as long as we know a pair of angle and the opposite side, right? So just to use my stencil here really quickly to do one out. So for example, if we have a triangle like this, and we know that, say, this angle is, I don't know, 48 degrees, and this angle over here is, let's say, 41 degrees. I know it doesn't quite look that way, right? Let's say that was 48 and this one over here was 41, right? And we knew this side or this side. Say we knew this side here was 7 centimeters. Now, thanks to sine law, we have enough information to find out all the rest of the sides of the triangle. Even though this is not a right triangle, so none of these angles are 90 degrees, which means we wouldn't be able to use excuse me. Actually, let's make that, let's call this 58 degrees. Let's call this 58 instead of 48. There we go. That makes it more accurate to what the sine law represents. Right? So if that's a 58 and this is a 41, we now have enough to find out all the rest of these, right? Because sine law tells us that A over sine A is equal to B over sine B, where this part here is we use a lowercase b, we use an upper and a lowercase to mean the two ones that correspond to each other, right? So an uppercase b is the angle that corresponds to side, which is lowercase b, like so, right? So yeah, let's go ahead and calculate it for this one, right? Mine's going to be a bit different than what it shows over there on the side, of course, but it can work for any acute triangle. Excuse me. And like I said, this is kind of similar to one of the previous topics that you've done, which is similar triangles, right? You remember in similar triangles, when we did those, we set up ratios of one side to another. Well, the math for this is very similar to that, but instead of one side to another, it's going to be one side to the angle corresponding to it, right? So here if I have 7 over sine 58, right? 7 over sine 58, because it's the angle in the side opposite, that's going to equal this unknown one over here, which I'm going to call x, going to be x over sine 41. Now what we've got to do once we get to this point is we had to solve this one to get x by itself, right? And here we're dividing by sine 41. So if we want to get rid of dividing by sine 41, we had to do the opposite, which is multiplying. So we're actually going to be multiplying both sides by sine 41. So that's how I'm going to write this out. Like this, right? So we're going to multiply those guys out like so. And then the sine 41 here and the sine 41 here are going to cancel. We're going to be left with 7 sine 41 over sine 58 equals x, like so. Then, over here, we're going to grab our calculator. So we're going to do 7 sine 41, that equals that amount, divide by sine 58. There we go. So 5.4 equals x. So that tells me that if this is 7 centimeters, 58 degrees, 41 degrees, x, right? The x over here is actually going to be 5.4. So how can I figure out the rest of this triangle? Well, of course I can, right? Because I could go ahead and then find this angle over here, this red angle, right? And I call that angle theta, and this is going to be side y. Well, we know that theta, right, the unknown angle that we have over here, is going to be 180, because that's the full measure of a triangle, minus 58 and minus 41. So that's going to be 180 minus 99, right? So that is then going to be 81 degrees. Right, so if I wanted to find side y, I could go ahead and I could use the same ratio, right? My 7 over sine 58. That's going to equal y over sine 81. Now I can go ahead and start figuring out those ones, right? I can do, again, I'm going to multiply the 81 across. So we're going to have 7 sine 81 over sine 58 equals y. And then you're just going to have to break out your calculator. 7 sine 81 divided by sine of 58. So I'll call that 8.15. Or 8.2. I'll round it to 8.2 equals y. So there we go. We know that for this triangle, if that side is 7 centimeters, this side is going to be 5.4, and this side is going to be 8.2 centimeters. Okay? Now, there is one other way of doing these ones that I want to show. It's not really another way, per se. It's just a minor different wrinkle in how we're going to figure these ones out. I'm going to draw my triangle a bit bigger this time, because using this one as a stencil makes a triangle that's perhaps a little small. A little small for our purposes of seeing it on stream. This is still going to be Math 3102C Unit 2. Say we knew, instead of knowing the angles and finding the sides like we did in the last one, say we knew the sides and we wanted to find the angles, right? Say this side here was 16 centimeters, this side over here was 10 centimeters, and this side over here was, 11.5 centimeters, right? I just picked totally random ones. And then say we knew this angle over here to be 104 degrees. Let's say we knew that. Actually, I'm not going to do all three sides. Hey, I'm not going to do all three sides. Say, let's forget that one. Let's forget that. I'm just pulling these out of the air, so I don't know that actually is going to work out. So instead of labeling that one to be 11.5, let's now this will work. This will work because I'll just this other side will just become whatever it needs to be for this to work. So, hold on. But anyway, how am I going to go about finding this angle over here? Right? We're going to call this angle I'm going to call this angle A. I'm going to call this one over here angle B. So how am I going to go about finding angle A? Right? Well, I know that the basic form of my sine law is A over sine A. Oh, right. Generally we use capital letters for the angle. Yes, my mistake. My mistake. So this will be a capital A, and this will be a capital B. There we go. Easy enough. Get some like Bart Simpson skills, turning one letter into another. D's become B's so easily, Bart. You don't have much respect for me, do you, boy? No, sir. I love that scene. I love how Bart says "no, sir" to Homer when Homer says, "You don't have much respect for me, do you, boy?" And Bart says, "No, sir." Right? Anyway, classic Simpsons is amazing. So yeah, to find side A, well, side A is over here, sine A, or the angle A, we can still go back and fill in the equation just the same as we would for finding the side. Just there's going to be one small difference at the end, right? But what we'll have is, say, 16 over sine 104, because that's the pair that we know, equals 10 over sine of angle A. All right? We don't know what angle A is, but we know that the side that corresponds with it is 10. So now we can go ahead and figure these ones out. One easy way to do it from the start here is we can take this and flip it, right? Because we know that if A over sine A is equal to B over sine B, we can just as easily say that sine A over A is equal to sine B over B. Now, for my money, I don't really think it's super important to list that out and explain it like so, just because. Do they show that over here? Yeah. Right? Just because from our algebra rules, we know that we can flip both sides of an equation, right? You can do that. You can take the reciprocal of both sides and it's still equal, right? So when you're writing out your basic form of the formula, I always keep the basic form like this, but you can write your basic form like this instead. But the important part, to my mind, is knowing that you can switch between the two. Like if we have this and we want to make this a bit easier on ourselves for workings, well, we can easily just call this sine 104 over 16 equals sine of A over 10. Just flip both sides. Now, I am trying to get sine of A by itself. So to get that by itself, I have to get rid of this divide by 10 here. So to do that, of course, I'm going to multiply both sides by 10, like this. And this is sine of A over 10 times 10. Now again, this is a little bit more pedantic than what you would normally do. You wouldn't have to necessarily have to do this. And instead of 10 over 16, how about we call this 5 over 8? Whatever. Right? So this is going to be 5 sine 104 over 8 equals sine of A. And it still says sine of A here, which might seem a little bit confusing, but we don't really need to concern ourselves with that quite yet, because we can take this still and turn it into an actual decimal number, right? So I'm just going to do that in here. Sine of 5 sine 104 divided by 8. It's going to be 0.6064 equals sine of A. Now, Esther, I can't remember if you have seen this operation yet, but you might have seen me do it on stream for someone else, even if you haven't. But all we have to do now is do the inverse sine. And we see on the calculator, on mine, it's right there. It's like sine to the -1 is what it looks like. It's usually going to be second function, which on my calculator is this, and sine. On pretty much every calculator, it's going to be that. Now, I don't know exactly what yours is like. If you don't know where to find it, you can, send me a picture of the calculator, and it shouldn't be that hard to find. It's usually going to be second function sine. And what that is, sine to the -1, it's the opposite of sine, right? So if this decimal equals sine A, then the anti-sine or the inverse sine of the decimal is going to give us the angle A. So I'm just going to take inverse sine of the answer. So I'm going to do that. It's going to be 37.3. So about 37.3 degrees equals A, or angle A. Right? So that's going to be 37.3 degrees, as we found out from down here. Now we can go ahead and get angle B, can't we? Right? That's not hard, right? Because we know now that B is going to be 180 minus 104 and minus. Remember to set the calculator to degrees and not radians? Yes. Thank you very much, Elf. That is an excellent point. That's an excellent point. On my calculator, that's over here, right, under degrees. Now, every calculator will have that. You'll have, oftentimes it's listed as DEG, DEG, RAD at the top, and you have to make sure it's on DEG. That's true, right? Because radians are a different way of measuring angles. I believe, yes, the academic math gets into radians, and I don't, the general doesn't. But 2 pi radians are equal to 360. 180 minus 104 minus 37.3. So B is going to be 38.7 degrees. Right? Because we just took this value and put it back in. Now that we have this angle, we can find this side over here. Right? So this is going to be side lowercase b. So let's find that. It's probably not going to be 11.5, the one that I put in at the start. But we can go ahead and find it, right? So I'm going to do that over here. So we then have our original. I'll use the original again. Actually, you know what? I'll start off with the sine 104 over 16. And that's going to equal sine of... All right, hold on. Never mind. Scratch that, reverse it. I was doing it right the first time. I was doing it because now we're back to finding a side again, right? Don't mind me. I am going to write it in this format. So it's going to be 16 over sine 104. That's going to equal our unknown, so lowercase b, over sine of 38.7, like so. Right? So now this one is back to being like it was on the previous page, because now we've got all three angles, and we're just trying to find our last remaining side. So we're going to multiply by sine of 38.7. So we're going to have 16 sine of 38.7 over sine of 104. That's going to equal b. Now we're going to go back on over to the mathematical Game Boy. 16 sine 38.7. It's going to get that value. I'm going to divide that by sine of 104. 10.3. Hey, I was... well, not that close. 10.3 equals b. So for this triangle to exist, this to be 16, that to be 104, and that to be 10, then we know that this side over here is going to have to be 10.3 centimeters, like so. Right? So Esther, that is just a quick example of how you're going to do sort of the two different takes on sine law. You will also have to do cosine law in this unit. I'm not going to overload you with too much stuff today and go over cosine law, but I will do that one in a future one, especially if you ask, right? I'll obviously do all those questions. And I did send you a video earlier that contains some more information on how to do those two topics as well. Right? So now I am going to introduce standard deviation really quickly. Standard deviation is probably the topic in math that I've taught in the most different settings. Actually, I taught stats to skilled trades, occupational health and safety, and to just business admin as well. And standard deviation is a super common topic in both those because it's a really, really practical topic, and it is important to know, right? And it's more important less to calculate it, although we are going to calculate it in this course, but more to understand what it represents. And I know that this is a little bit out of order compared to what it's actually showing you in your book, Betty Ann, but I am going to introduce a normal distribution first en route to doing that one, basically. All right, so let me go back over to the document display here. Normal distribution, like I said, is section 2.4, so it's after the standard deviation. But for my money, it makes a lot of sense to understand this first. So normal distribution is what we call the bell curve. You've probably heard about this before. Sometimes you'll hear of like teachers grading on a curve. I guarantee you that does not happen. It does not happen here, at least not in this program. And it doesn't happen as often as you might think. Even when it does, teachers honestly really shouldn't admit that they're doing it. But this is not a pedagogical class, right? Although I would vehemently argue against grading on a curve in any sense, right? Because to me, the notion of grading on a curve is this idea that any class should roughly have this sort of a normal distribution of marks. Most people should be around the average, around the middle, right? So if this, say, is a C here in the center, so then you should have 34% or 68% of people should be around a C. Then you'll have about, this 13.5 or so up into a B, this 13.5 down into a D, then this like 2.5 into A's, and this 2.5 into F's, right? To my mind, that's like, anyway, that might be a bit of an odd digression there, but I strongly disagree that is a way to grade courses, and to me it seems like a misunderstanding both of statistics and of teaching. But anyway, I'm not here to train other people on how to teach courses, so maybe I'll spare a bit of that right now. Um, but the normal distribution here, for very, very, very large quantities of data, the normal distribution is generally really accurate. That for the bell curve, or the normal distribution, tells us how far away from the mean most values are going to be in a large set of data. So it tells us here that in general, you're going to have 34% of data that's going to be within one standard deviation of the mean. Now, what is a standard deviation? Right? Well, a standard deviation is a measure of how spread out your data is. The larger your standard deviation, the more spread your data is, right? Because say if your mean, say, was 15 and your standard deviation was 5, well, one standard deviation up is going to get you to 20, one down is going to get you to 10, right? And then you go down another one, it gets over here. And it says that another 13.5% is between one standard deviation down and two down. Another 13.5 between one up and two up. It doesn't really, I know we're sort of jumping in kind of in the middle here, but this graph, right? See these symbols down below? This here, mu is the mean, right? So this is, I'll just label this for my own purposes so I know who to send these notes to. So this is 2101B unit 2, right? So mu, this symbol, means the mean, right? And then this symbol here, which is, I believe, what letter is that? I can't even remember. Is that a lowercase sigma? I don't actually remember what Greek letter that one is, but that one is a standard deviation. So standard deviation measures the spread of a group of numbers, right? So the more spread out the numbers, the higher the standard deviation. And of course, conversely, the more dense the numbers, the closer together they are, the smaller the standard deviation is going to be. What it actually is it's the average amount that a random number in a set is going to differ from the mean of the set. Is kind of how we can think of the standard deviation. Standard meaning the average, and deviation, meaning how far apart it is from the other numbers, right? And the normal distribution over here, it is an oft misunderstood sort of notion, right? But it's a very good statistical model for large groups of numbers. Large groups of information tends to be normally distributed, which means within one standard deviation of the mean, you're going to get 68% of your data. Within 95% from here to here, 95% of your data is going to be within two standard deviations of your mean, and about 99.7 is going to be within three of the mean. And you can see how it goes here, right? This concept also brings in calculus and stuff as well, right? I do love how stats is kind of a summary of a lot of the different math that you look at. But if you look at the area under the curve or the space under it, you see that the space under is very big in this first section, but gets a lot smaller as it goes on. And that represents there being fewer numbers, fewer and fewer numbers, the further away you get from the standard deviation. But what I wanted to focus on first is how we calculate it. Now, to my mind, like I said at the start, right, it doesn't really make a whole lot of sense to just jump in and looking at how to calculate the standard deviation without really knowing what it is you're figuring out. And what we're figuring out when we look at the standard deviation is, like I said, how spread apart a group of numbers are. So the standard deviation is going to equal the square root of the sum of each number subtract the mean squared divided by the number of numbers that there are. Boy, oh boy, that's quite a mouthful. It really is, right? And a lot of the time when you're doing any sort of statistical analysis, your standard deviation is going to be calculated by a calculator, like Excel or a TI-84, or all these calculators are extremely quick at calculating standard deviation, whereas a person is extremely slow at it. However, for the course that you're doing right now, we actually don't do any of the technology ones. Now, you're totally welcome to, and I'll show you on stream, maybe not today, because I want to get to this part and then just move on. But it's super easy in like Microsoft Excel. You just use the stdev function, and you just pick a bunch of numbers, use stdev S or P. I'll go over the difference of that some other day. But then it just figures it out for you, right? But here, we're going to have a fair bit of number crunching. And as you see down here, right, this is the table that we're going to need. First, we have to get our data values. We have to find the mean. We have to find the difference between each piece of data and the mean. We have to find the squared difference between the data and the mean. Then we have to take the average squared distance. And then we had to take the square root of the average squared distance difference. Boy, oh boy, that's a lot of words, right? So what we're going to need is, first up, we're going to need a table. Table like this, right? So we're going to need our values. I'm going to pick one of the ones from the book here now in a second. We're going to need our values there like that. We're going to need our mean, right? Which is mu. We use mu to represent the mean. Difference, right? Square difference. Okay. And we're going to need that fill those into a table normally like this. Then after we get all that, then we're going to get the sum or the total of the squared difference. Okay? But yes, there are just this many steps to it. It is a labor intensive sort of math that we're doing, and that's why when we look over, hold on a second, I thought I had the textbook open. I do. Okay, so when we look over at the textbook, like here, it pretty quickly tells you like just use technology to do it, right? Because they're using fairly large sets of numbers. I mean, look at this set of numbers, right? It's finding the standard deviation of each of these sets is a bonkers amount of work when you're doing it by hand. We are going to be doing it by hand in this course. I know, groan, right? But hey, it's really not that bad when you get used to it. It's just a bit labor intensive, and all the examples that you're going to be doing in this course, Betty Ann, are fairly small sets of numbers, and that's because the course is designed for you to be doing them by hand. So like it says, I'm going to do page 261. So this is page 261 in the textbook, and this is going to be question 1A. And it's asking us for this question to determine by hand the standard deviation of test marks for the two chemistry classes shown. Verify your results using technology. I'm not going to do that part. I'm just going to... which class has more consistent marks over the first 5 years, and explain. Okay, so we've got two different sets. So I'm going to do class 1. Class 1 I'm going to do here in green in this set. Right? So let me just zoom in a bit here. And tell you what, I'm going to switch over to this display. So I've got a bit more room. Zoom in a little bit more. There we go. Yeah, not bad. So our values are going to be, for the first one, 94, 56, 89, 67, and 84. Right? Well, we know that the mean is going to be the sum of the numbers divided by the numbers. Right? Sigma, this capital E, this capital Greek E, basically. That means the sum of n divided by the numbers, right? So the sum of the numbers here is going to be 94 plus 56 plus 89 plus 67 plus 84 divided by 5. I probably didn't need to write that out for you, right? But I'm going to be very, very pedantic for this one, because this whole unit, really, doing stats like this by hand, is just number crunching. But it is important to model all the individual steps of said number crunching, because it's going to take a little while. So that is going to be 78. Okay. So now the mean. You don't really need a full column for the mean, honestly, right? You could just jump straight to the difference, right? But this is going to be so the mean is going to be 78. I'll use different colors for each one. 78, 78, 78, 78, and 78. One reason this is a good example, right? So we have 94 minus 78. It's going to be 16. What about this next one? 56 minus 78. Can we do that? Negative 22. Is that okay? Is it okay to have a negative? Absolutely it is. Absolutely it is okay to have a negative here. Why is it okay to have a negative? Well, it's okay to have a negative because of this bit, right? Because when we take this negative difference over here, right, and we square them, remember when we square a number, it always becomes a positive. Right, so this one here is going to be 256, one of the best numbers in the world. Not my favorite number, not literally my favorite number, right? Because that's 52 factorial. But 256 is a good one. Like I got to say, 16 squared, 256. Or that's, more importantly, 2 to the power of 8. It's a great number. 22 squared, I don't know off the top of my head, although I should. That's 484. 11 squared is 121. That's another 121, and that's a 36. So there's our square difference, right? So, so the square difference is otherwise known as, let me just fill in here. So this is the same as the x minus mu squared part of the formula. See that over here? X minus mu squared? That's the same as the square difference. And the total is otherwise the sum of x minus mu squared, right? That's the total of these, and that's going to be, boy, (1018) over here. And we know that to get onto our full standard deviation, we now, what we're looking for, right? Our standard deviation is going to be the root of the sum of x minus mu squared over n. So we know that the sum of x minus mu squared is 1018. So that's going to be 1018 on top. N is still the number of numbers, just like it is over here. Just like just that n, it's the same n. That's going to be over 5, right? So I'm just going to go up here. So now what we have is standard deviation is equal to the root of, I don't know 1018 over 5 off the top of my head, 203.6. And then the square root of that, we're taking the principal square root, of course. So the standard deviation is about 14.3. So what this tells us now is that on average, these marks are 14.3 different than the mean. Right? And we see some, right? This one, the difference is higher. This one, the difference is quite a bit higher. A little bit less, a fair bit less. But that's sort of what we would expect, right? Because we expect some pieces, we expect it to roughly even out, right? This is a little higher, a lot higher, a little less, and a bit more or less, right? All right, so 14.3 is our standard deviation for that one. And I'm going to go through and do the next one as well, just to finish off calculating this one by hand, right? So this is still going to be math 2101B unit 2. And this is still going to be page 261. This is going to be still 1A, but I'm going to do the other set of numbers now. I'm going to do class B. So I'm going to have the, let's see, I'll draw my line across first. And we do have to do it a table like this every single time. I know it's a pain. Value, and then the mean, and then the x minus the mean, and then the x minus the mean squared is going to be over here. All right, so our values are 84, 77, 76, 81, and 74. Even just from glancing at it, those ones look a lot closer together, don't they? They look quite a bit closer together than the others. But let's go through and let's calculate our standard deviation. This one down here is going to be the sum of x minus mu squared. It's going to be down here. Now, we do need to find out mu, or our mean, first, right? So our mean is going to be the sum of n over n. So mu is going to be, I'm not going to write them all out this time. I'm just going to add it together. 84 plus 77 plus 76 plus 81 plus 74. 392 divided by 5. So then the average mark, or the mean, rather, I shouldn't say the average because it's only one of many averages, is going to be 78.4. Let's make sure I added those correctly. 84, 77, 76, 81, 74. Yes, okay. So that's totally fine. We can have a decimal value here. It's just going to make, it makes it maybe a little bit more work for us, but, it's effectively the same. It's just one more digit to write out. Okay. So 84 minus that one, 5.6. This is going to be a negative 1.4. This is going to be a negative 2.4. This is going to be a 2.6. Yep, 2.6. This is going to be a negative 4.4. Yeah, that's right. That's right. Okay. Now, I don't know 56 squared, or 5.6 squared either. That's going to be 31.36 over here. 1.4 squared, 1.96, 2.4 squared, 5.76. I mean, you're seeing now, I guess, probably why we have these ones done by computer most of the time. Because even for a set of numbers with 5 data points, which is a really, really, really small set of numbers, like statistically, a set of 5 is practically useless, right? Because it's not nearly enough information to be able to really draw any sort of meaningful conclusions. Okay, so the sum is going to be 65.2. Okay, so now remember that the whole standard deviation is going to be the root of the sum of x minus mu squared over n. Right? If I wanted to be really proper, I'd do my, there we go. Get the real nice serifs. Get the serifs on my sigma. That's good. So the standard deviation is going to be the root of 65.2 divided by 5. Right? So it's going to be the root of 65.2 divided by 5, 13.04, the square root of that answer. So standard deviation is just going to be about 3.6. Right? Okay. So now if we look back at the previous one, which I still have here on this other sheet of paper, that I just crumpled a little bit accidentally, we see that the standard deviation of the first class is 14.3. Standard deviation of the second class is 3.6. Well, that's a big difference, isn't it? And we can see over here on these numbers what that represents, right? I mean, look at class 1, or class A, sorry. A person got 94, a person got 89, and a person got 84. Those are relatively clumped together. But then another person got 67, another one got 56, right? So there's a big difference between 94 and 56, right? Or even between, 89 and 67, there's a big difference. So class A is quite spread out in their marks. Class B goes between 84 and 74, and all the rest of them are in between 84, 81, 77, 76, 74. Class B had a really clumped results, right? And that's why we see that the standard deviation for Class B is 3.6, whereas the standard deviation for Class A is 14.3. Because it measures, like I said, the average difference between each individual data point and the mean data point. Okay. What else did the question ask us to figure out? Verify results. Which class had the more consistent marks over the first 5 tests? Well, instead of sliding it back and forth to read, maybe I'll zoom out a little bit. And for anyone who needs to interpret statistics as part of their job, right, does really need to understand standard deviation. Not necessarily how to calculate it, because, like I said, technology will take care of that for most people that are using this stuff in their day-to-day lives. But it is still really important to understand what standard deviation means, right? And it's a measure of how spread apart your numbers are, which again is one reason why it needs to be taught in courses like occupational health and safety, right? Because being able to accurately read and interpret statistical analysis is a massive part of knowing, like what new controls will make a workplace safer, something like that, right? Or what sort of trials have had meaningful results from them, right? Anyway, so that's an introductory look then into standard deviation. So that, yes, that gets through all the topics that I wanted to cover today. Standard deviation, sine law, and angle properties. All right. Leave you with one more look of St. John's, the Narrows here, with some seagulls flying over it, and this battery of cannons ready to obliterate those seagulls. Anyway, um, yes, another nice look out past the Narrows here. Like I said, another day. If we kept on going, you see the sort of middle top of the screen there. There's a little piece of land sticking out. If you kept on going past that, the next thing you'd hit is France, and it'd be a long ways. quite quite a steam directly across the ocean there. But anyway, yes, thanks for being with me today. I hope that was entertaining and engaging and informative. All right. As always, please do let me know if you have any questions. Any students in my class do have my email, so you can drop in there if you have anything that you want me to cover. Right? Like I said, thanks for being here. Stay safe, and I hope to see you all again tomorrow.